starting recording just to test it. And anyway, so we talked about nuclear chemistry, chapter 3. Chapter 3, we finished most of the stuff there. What we have really to know in chapter 3, there are some topics. The first one here is in the nuclear chemistry. That's chapter 3, by the way. So this is chapter 3. So what we need really to know, types of radiation. Types of radiation. This is very important. And as we covered that online, we have a couple of those. We have alpha, beta, gamma, correct? And we have proton, we have neutron, correct? So we have proton, neutron, and positron. So those are 6 types of radiation. And that's very important to know that we have 6 types of radiation. And those, we have to know their atomic mass of each radiation and the atomic number, which is said to be in nuclear chemistry charge. So if I say alpha here, alpha is nothing less than just helium atom. Atomic mass is 4, atomic number is 2. Beta, those are electrons coming from the nucleus, not the valence electrons, not the actual core electrons. Those are just coming within the collision disturbance inside the nucleus itself, between protons and neutrons, correct? So this is the beta radiation has no masses. So atomic mass is 0. The charge is -1. Gamma, on the other hand, gamma does not have any mass, does not have any atomic number, any charge. Okay, guys? So those are the 3. The protons here, it has a mass of 1, atomic mass of 1, the mass of it's 1, atomic number is 1. The neutron, it does have a mass, 1, but has no charge, it's neutral. Atomic number is 0, correct? Atomic number is 0. And then the last one is the positron, which is the opposite of beta. It has a mass of 0, however the atomic number is +1. It does have a charge. Atomic number in this nuclear chemistry we call charge. So those are 6 types of radiation we have really to know. And I think we took uranium and we took iron element, and then you can say this is the first type of the first important section of nuclear chemistry. So chapter 3 is about nuclear chemistry. The second, which is the most important of all after knowing those radiations, is the balancing nuclear, not chemical, balancing nuclear equation. So if you allow me, I'll take this one here. I'll go for the second one. Everybody has this? Everybody has this? Everyone? Okay. I want you to wait a little bit. Wait a little bit. Second important topic in nuclear chemistry which is very, very important. I mean, especially if you go further for any health-related stuff, you will know they have a very bad effect on the health. Those radiation can cause a lot of problems health-wise. Okay, so especially gamma. Balancing nuclear equation is totally different from the balancing chemical equation, which will have the next chapter is balancing chemical equation. But this is balancing nuclear equation, which is totally different from whatever we have seen before, in the sense we are looking equations here. We are looking at the atomic mass is at the left side of the nuclear equation, has to equal atomic masses at the right side of the nuclear equation. And the atomic numbers at the left side of the nuclear equation has to equal what? The atomic numbers of the atoms at the right side of the nuclear equation. So pick up for me any elements you want. Give me its atomic number, atomic mass. As I said, we go for up to 4 in this class. So because it's just an introduction to chemistry, we'll not go for higher. But you can take any elements, even high element. We went through uranium, which has atomic number 92, atomic mass 235. Uranium has 2 isotopes. Uranium has 2 isotopes, 235 and 238, 235 atomic mass, and the other one atomic mass 238. So pick up for me any element in the periodic table. Give me the 2 important characteristics of the element, which is atomic number and atomic mass. So pick up any element. Somebody will pick up. Look at the periodic table. Copper, okay. The copper, somebody said copper, okay. The copper here has a symbol is Cu. Capital C, always the symbols are, the first alphabet is capital, the second alphabet is small. And they cannot exceed 2 alphabets. So you don't see an element that has 3 alphabets. No, all the elements are 1 or 2. That's the maximum number of alphabets of the element. So what is the atomic number of copper? Look it up. The atomic number always the smallest number, correct? 25? 29. That will be at the bottom. What is the atomic mass? Roughly it will be the double of it, correct? How much is it? 63.64? 54? Okay, so here it is. 63.54. Now, when it comes to balancing chemical equation, you are dealing with the number of electrons, I mean the beta from nucleus, number of protons or positrons, all those, they are whole units, no fraction. So therefore we'll say, because 63.4, we'll say copper will have 64 instead of 63.5. That's when we have to know the whole number. We have to put the whole 63.54 atomic mass into whole number, because you don't have fraction of those particles. The particles are whole units. When I say positron, that's a whole unit, no fraction of it. Okay, when I say alpha radiation, the helium atom, atomic mass is 4, atomic number is 2, no fraction, correct? So therefore 29. Now this is the copper we'll be using, and see what types of elements we are getting when these 6 types of radiation coming off this copper element. So let's do it together. We'll do 3 and then we'll do the other 3. So copper, 64 atomic mass, 29 atomic number. First we'll go for alpha radiation. Alpha radiation is helium. Helium is atomic number is 2, atomic mass is 4. So what is the next is, what is the elements coming here? I'll say this is X. Let's get our X here. That's the element. That's what you get in the final exam, that we will be getting in the next quiz and exam. So the X, we say nuclear chemistry balancing is different from normal chemical equations balancing. This one here, we balance the amount of atomic number at the left side of the equation equal the amount of the atomic number at the right side, and the atomic mass at the left equal atomic masses at the right. So here is 2, correct? So what will be at the bottom here? How much? 27. Why is 27? 27 plus 2 makes what? 29. Correct? Everybody's following me here? So what will be in the top? We have 4 here. So then will be what? 60. So if you add those here, it has to come to 64. Perfect. So now I want to know what the type of elements. So I go by the atomic number. That's the only way I can recognize any element. Atomic masses are differing from each other because of the number of neutrons. However, that's atomic masses. Atomic number does not change. Therefore, we can recognize our element by the number of the atomic number. So 27. Now we have copper is 29. We went down 27. So what is the element 27? Cobalt. So I will say, now take this one here and take this one out. Okay, guys, so my element is cobalt, capital O, small, capital C, small o. This is 16 the top, atomic mass, and this is 27. So this is cobalt. Okay, guys, make sense? That's the alpha radiation. If copper by chance giving off alpha radiation, I'm producing out this cobalt new element. Out of this copper, new element is cobalt, and that's what in the industry, cobalt comes in the nature as an oxide. But if you have a rare element and you want to produce it, you have to go through nuclear chemistry. This is the way we can produce it. So cobalt is not a rare element. Cobalt is found in abundance in nature as an oxide or a salt. So, but that's the way we can produce new elements in question or in need or in demand. That's we produce. So let's take, now that's the alpha radiation. Let's take beta radiation. Can I take this one out? Everybody has it? Okay. Let's take, I'll keep the cover here, but I'll take all this out and then we'll see what will happen if we have beta radiation. That's alpha radiation, correct? So let's see if we can get okay, so this is 64, this is 29, this is an arrow, and alpha is, we said helium, correct? Atomic mass 4, atomic number is 2. Beta, on the other hand, is like an electron coming out of the nucleus, not from valence electron, not the core valence outside the nucleus, not the electrons outside. This is coming from the collision between protons inside the nucleus and neutrons, correct? That's what's inside the nucleus. So has a 0 atomic mass and has a charge, atomic number is -1. So what will be my X new element I'm producing? Somebody will tell me? What is, the question is, what my new element will be? What's the atomic number of it? 30, perfect, thank you. And what will be the atomic mass? What is it? 64. So X equal to what? Again, I go by the atomic number. What's the atomic number of 30 here? Somebody will tell me, 30? zinc, correct? After copper, zinc. So this is Zn. This is zinc. Atomic number is 30. That's what we can recognize an element by its atomic number. So if copper will give off beta radiation, it produces a new element called zinc. Okay? And that's the way in the industry. That's they manufacture rare elements through this way, through nuclear. Not the ones are abundant. Copper is abundant in nature. Zinc is abundant in nature. Aluminum, those are there found in nature. They don't need to go through this. Correct? This way of producing elements is very expensive. You do it only for very rare elements, metal or non-metal. Correct? So can I take this one out? Now we have alpha, beta. Let's do gamma. Okay? So gamma here has the only radiation, see, does not have any mass, does not have any atomic number, no charge. Here nuclear chemistry, atomic number is called charge. So the only one does not have a mass, does not have a charge or atomic number, is gamma. And therefore gamma can go through walls, okay? Can go through objects. Gamma can go through objects easily, very easily. But the other ones, they do have if they have a mass, they will collide and they will bounce off back to you, correct? So gamma does not have a mass at all. One does not have any charge. So we are producing what here? What the element will be here? Copper itself, yes. Copper itself. So copper itself will be produced. So we'll give off the 64 here and 29, because if you add those, it will be the same thing. So X is copper 64, 29. This is copper. Okay? And the only radiation, the only non-radiation, correct? And matter is made of two items. Matter is made of two items: particles and waves. Waves does not have a mass. It can go through objects, correct? If somebody transmitting from downtown a radio, I am here. I can pick up the radio, correct? So all this wavelength here of this radio from here to all the way to downtown, that's the length of the wave. But the wave has the characteristic of going through objects. But particles, they can't. They bounce when they collide with any object, and they bounce back to the source, correct? So therefore they are not. So let's take, we have taken alpha, beta, gamma. Let's take a proton. Okay, we'll take a proton now. As I said, remember, gamma is the only thing that goes through. It's a wave. All the other ones, particles coming out of this radiation, all the radiation producing particles. Although they are almost zero masses, but still they have a charge. They can bounce back. So let's take, we said what, protons? Protons H, atomic mass 1, atomic number or charge is +1. Nuclear chemistry is atomic number is called charge. That's +1, correct? So what will be the element here? Atomic mass, how much? Somebody will tell me? How much is it? 63, perfect. And atomic number or charge? 28. So what is X? So we'll go for the 28 and look. 28 is what? Somebody will tell me 28 is nickel, correct? Nickel wave. Now, we don't care about atomic mass because nickel will have what? Different isotopes. So atomic masses will change accordingly. So this is nickel, correct? So if copper will give off a radiation of protons, then the new element produced is nickel, correct? So that's, as I said, rare elements are produced by nuclear reaction. It's very expensive, but that's the way you can produce them. Okay, so next we'll take neutron and then positron left. So let's take any questions so far? Any question? Ask, please. Any question? Because that's the whole chapter 3, by the way. So that's the whole chapter 3. And then just a little bit of application. That's the whole chapter 3. It's a very simple chapter. So let me take this one out. Take this one out.
Question?
Yes.
You said something bouncing back, like
Bouncing back, for example, proton. A proton is a particle, has a mass of 1, correct? The concrete has a mass. So you cannot expect protons or alpha or beta to go through and come into the other classroom. No. They will hit inside, they will be absorbed a little bit, and then they will come back. It's like a ball, plastic ball, you throw it and then come back to you. That's what the radiation. But gamma is totally different. Gamma is going through the wall, through the concrete, through whatever, it will go all the way, it go in the space, so it will further, it will not stop. Anytime it collide with an object, go through that object. Because it's massless and it's a wave. The same thing, I can see a TV station from thousands of miles far away. How? Those are waves. TV, radio waves, TV waves, all those are waves, microwaves. So all those waves, they can go through. X-ray waves, those go through. So X-ray, gamma, microwave, X-ray waves, gamma waves. Those are waves, they can go through the object because they don't carry mass. But as soon as they carry mass, they will collide with this object. They might be absorbed, they go inside a little bit deep inside, but again, they have to be bounced out. They cannot go through the object. Make sense? Yeah. So let's take now the positron and then the neutron. Let's take the neutron and see what we are producing out of the neutron. So the neutron is, believe it or not, has a mass. But since it's neutral, has no charge. Remember, in nuclear chemistry, charge is atomic number. That's equivalent. Atomic number means charge. Charge is atomic number in nuclear chemistry. So it does not have a charge, does not have atomic number, but it has a mass. So the elements we are expecting to be, somebody will tell me? The element we are expecting to be, what will be the atomic mass of it? Come on, guys, you can tell me. 60 what? 63, because 63 plus 1, 64. However, the atomic mass remains what? The same, because 0 here, this is 29. So our X here, our X is equal what? Copper. But this time an isotope of copper, because the atomic mass is changing, 63, 29. So that's another isotope of copper. So we produce another isotope. Why isotope? Because they have the same atomic number, but they charge atomic. They differ in atomic masses. One is 64, one is 63, due to the number of neutrons. Correct? Due to number of neutrons. So that's another copper, another isotope of copper. The last one is positron. Any questions so far? Any question, guys? I will try to upload this as near the other one as well. So, any question about this? Any question? Okay, let's take the last radiation, which will say it's a positron. Okay, positron is the opposite of the beta. It's the opposite of beta. Beta has no mass, however, it has atomic number or charge of -1. The positron has the same. It's like electron, but opposite what? Charge, or atomic number is +1, 0 mass. Correct? So our X will be what? Remember, that's 29 here, guys. So our atomic number will be what? Or charge. How much is it? 20 what? 28. And the atomic mass will remain as is because this is 0, 64. So now here our X is equal to what? What will be, again, you have to look at always the atomic number here to visualize the element. What is the 28? The 28 is what? Nickel. That's another isotope. Remember, we got nickel somewhere in the process as well? This is another isotope of nickel. So this is a nickel, second nickel here. So nickel, Ni, with the atomic mass 64, correct? And the atomic number is 28. 28 here. Correct? So that's the most important part of the whole chapter. Okay, guys? Number 3 is the application of nuclear chemistry. Number 3, we have to know the application of nuclear chemistry. Can I take this one out? Can I take this one out? Everybody has it? Everybody has it? Okay, so let's take this one out. And the topic in the chapter 3 is application. Or applications of nuclear Well, nuclear chemistry can be used in a peaceful way or harmful way. So it depends when and what you want to use it for. So that's the problem. So in a very harmful way, you can produce nuclear bombs out of this, correct? So here it is. You can use it in a harmful way. You can produce nuclear But don't come to the conclusion this nuclear chemistry is bad. No. Nuclear chemistry is the only chemistry we know that really fights tumors, all types of tumors, cancers, very efficiently. So, which is the most important part here, is really fighting tumors. So, fighting tumors, all types. Especially what? Gamma radiation. Gamma radiation. Gamma radiation, when you hear about somebody will tell you somebody has cancer and he gets radiation. So this radiation is gamma radiation. Small, tiny dosage, small, tiny amount of gamma is with the beam. It's like a laser, small, tiny beam. It's radiation. And it's really pointed to a tumor. The location of tumor is known, can be traced, and you can see it. So you can just bombard this tumor with small, tiny gamma radiation. It goes through because it goes through the whole body. It goes from the other side. So, and it kills those tumors inside the body. Now the dosage is very critical because you don't have to add too much of the dosage, because what will happen to the patient will be barbecued, correct? It's highly energetic, high temperatures. So we will be barbecuing the patient. So it has to be very, very tiny and very, what they call it, very, the direction of it has to be really very, very good. Not you kill some healthy cells inside the body. You know where the tumor, you just pinpoint the radiation, gamma radiation to it, and it will kill that tumor, correct? So it will kill that tumor. So those are the two major applications it can be used in the military in a way, and it can fight tumors, especially gamma radiation. The alpha and beta and the other ones cannot fight tumors because it cannot go through. Gamma can go through the body and goes out the body, so those will bounce inside the tumor and will be absorbed by tumor, bounce back. The other radiation, because they have masses, they can't really fight tumors. The only thing will fight tumors is gamma radiation. It can go through. Or X-ray. Those are waves. All the waves can fight tumors, but not the ones that have masses. They will bounce back to the source. Okay, guys, that's the whole chapter. See, very, very short chapter. It's not really difficult, and mostly they are concerned in the final exam about balancing nuclear equation. So, any question about chapter? We'll go for worksheet for balancing nuclear equation. So, any question? Any question, guys? No question? Okay. So then let's look at the I opened for you here. So pick up any one of those and let me which one you like, and then we'll open it. Don't pay on those worksheets any money. Those are free, mostly done by retirees. Okay, so those are for free, so nobody will charge. So, and mostly universities related. So which one you like? So what's that? First one. Okay, the first one. Okay, yeah, this does not have any answer. That's a good thing. So let me just. Okay. So let's do a couple of those, and then we'll conclude chapter 3. We'll go for chapter 4. As I said, chapter 3 is the smallest ever chapter, and most probably they will ask in the final exam about balancing nuclear equations. So let's do pick up any of those and tell me any one of those from 1 to. We'll make a couple of those, so 2, 3 maybe. Let me see how much they are. Those are 11. So let's do 11. Those are 11. Let's do most of them. Say 5. Which one from the 1 to 5? We'll do a couple of those. Which one you like? The first one? Okay. What will be then? Here, what will be the elements? So what is coming out? What's this type of radiation? Beta radiation, correct. If it's +1, that will be what? Positron, correct? That's beta radiation. So what will be the element then here? What will be the element here? Somebody will tell me? What's the element here will be? X. What's the element here? What's the atomic number? Come on, guys, don't let me down. 2, correct. And the atomic mass, how much? 3. So what's the element is what atomic number is 2? Come on, look it up. Helium, correct? He, helium. Atomic number is 2. We go by the atomic number that will give us information about the element itself. So the answer is helium. Atomic mass is 3. It's another isotope of helium. Here in the periodic table we have helium is 4, but now we have found it says another isotope, the atomic mass 3. And atomic number does not change. Isotopes changing in atomic masses, but not in atomic number. So next, what will be happening in the second one? So can I take the first one out? Can I take the first one out? Everybody has the first one? First one? Take it out? Okay, let's take this one out. That's helium, another isotope of helium. So the second one, let's do the second one. So what will be coming out here, X? What's the atomic mass in the top? Come on, guys. Today is Monday or Tuesday? Yeah, Tuesday, so you have no excuse. If it's Monday, I'll say, okay, you are coming from the weekend, tired. But now Tuesday, not Monday. So what will be the atomic mass at the top? 4, correct, thank you. You made my day. 4 plus the 228, if you add them up, will make what? 232. Atomic masses at the left equal atomic masses at the right. Atomic number at the left equal atomic number at what? At the right. Left and right atomic masses equal. Left and right atomic numbers are equal. So what will be then here? 2. Our element is what? Helium. Atomic mass, that's another isotope of helium. The previous one was 3, correct? So this one here is helium. Atomic mass is 4. Previous one, atomic mass was 3, another isotope of helium. But the main thing is this one is not changing. Atomic number is not changing. Atomic masses do change, okay? And that's what we have isotopes. So can I take this one out? Let's take 3. Take the second one out. Everybody has it? Everybody has it? Okay. Good. Let's take. That will come 100%, not 100 trillion or gazillion percentage there will come. You should know how to balance nuclear equation. So that's, especially if you go health-related stuff, you will know that nuclear chemistry is used heavily in fighting cancer. All types of tumors are killed by gamma radiation. So, number 3, what will be here? X. What's the atomic mass in the top? 0. Correct. Perfect. What's the atomic number in the atomic number or at the right side? How much is it? -1. What is this with the atomic mass 0 and atomic numbers -1? This is what? E0 -1. This is what? Beta. I heard beta, correct? Correct. That's beta radiation coming off. Correct? So we are producing an element with PR, correct? And beta radiation coming off. Okay, so can I take this one out? Take it out? Okay, let's take this one out. How about number 4? What is this one here? Number 4 here, guys. This one here is what? What we call this one here? What's that? Beta. What's the opposite of beta? Positron. What's the opposite of beta? Positron. Both of them atomic mass is 0. However, beta is -1, and the positron here is what? +1. This is positron here. Positron. Okay, guys? Positron from the word positive. The beta has negative. Positron is like beta radiation, however, it's positive, positron. Positive. So, what will be our element coming here? What's the atomic mass? Will be what? 65, the same one. Okay. Now we are dealing with professionals today. That's good. It's not Monday. It's not Monday. That's excellent. So what will be the atomic number then? 20 what? 29. 29 plus 1 here is 30. What is the element here is with the atomic number 29? Was it? Was copper? Correct. So this is 65, and this is Cu. That's copper. Okay, guys? Okay, so we can leave this one here. Let's do 5. What will be coming out of X here? The top atomic mass will be what? 0. Atomic number is what? Plus 1, correct? I put it plus 1. So X will be what? X will be our 0 plus 1. This we call it what? Positron. It's positive. It's like beta is negative. This is positive, positron. Okay, guys? So I think by now you are very professional at that. Let's take a couple of those. I want to jump to the 4th chapter, and then you are still having some problems with this balancing. It's very important, especially if you go for health-related stuff. You learn about all this type of radiation killing tumors. You'll get the idea how the whole thing is working. And there is equipment in the hospitals with the gamma radiation to kill those radiation to kill those tumors. So, can I take this one out? Everybody has it? Okay, let's take this one here, and then you tell me next here. Okay, let's take the whole 11, and then we'll conclude the whole chapter. Let's do the whole 11, and then I'll be really satisfied that you understood the whole thing. So what will be our X here? So there is a beryllium 7 and 4. So this one is what? Zero mass, okay. And how about the atomic number? 0. So what is this one? X is equal what? Gamma. Gamma, 0 atomic mass and 0 atomic number. That's gamma. Okay, guys? So next, number 7. So we have neutron. You are bombarding the neutron, the nucleus. You are bombarding neutron 235. That's a major isotope. The other isotope 238. So the major one is 235. That's what you produce nuclear bombs out of it. So that's the most abundant one in nature. So atomic number is 92. Atomic mass 235. You bombard it with the neutron. What you are producing here? What is your X? What's your X? Come on, guys. What's the atomic mass of your X here? This is 1, guys, correct? This is how much? 235. What's the atomic mass will be? 2, 3, what? 6. Yes. 2, 3, 6. You have to add those up. The atomic masses, they have to be adding themselves up. How about the bottom? How much is it? 92. So we are not producing anything else, the same element. It's just when you are bombarding the neutron with the uranium, you are producing, let me take this one here, X out, another isotope of uranium. 92 atomic number, which is here, and 236, another isotope of uranium. Now this one here, uranium here is not stable. It will give of 3 things. 1, 2, and 3. What is the third one? What is the third one? What is the third one? Somebody will tell me. Remember, guys, this one here is 2, 3, 6. So how much is the sum of those two here? How much is it? Come on, guys. What will be the atomic mass here in the top? Here, I'll give you here. Look. You have 2, 3, 6, negative 1, 4, 1, negative 92. What will come out? That's positive here. 236 minus 141 minus 92. How much is it? Somebody had calculated? 3? Somebody said 3. Okay. How about the bottom here? This is 3. How about the bottom here is 55, correct? Negative, minus 37, and the bottom here plus 92, because here is 92, correct? Plus 92. What will be the bottom? That's the atomic number. So what will be? 92 plus minus 55 minus 57. How much is it? 0? No. 0, 5 plus 7, 2, 2, and 0. Yeah, that's correct. 0. Are we sure that's correct? 55 plus 73. That's 22 and 9. Yeah, 92 does 0. So which element is 0 and 3 on the top? Do you have an element that's 0 atomic number? No. This is meaning the charge is 0. So the charge is 0. So the charge is 0. So can I take this one here and play it around? I say, okay, how about if I put this one here? 3 neutrons. 3 neutrons. Is this equal this one here? Because we know that we don't have this particle. But if I put 3 in front and put neutron n, does it equal each other, correct? Correct? So then we have, that's the coming out here with the 3x in the top, 0. As soon as you see it like this, has to be a neutron. Neutron has no charge, correct? But it has a mass. And 3 of them, there has to be 3 neutrons coming out. So therefore, I'll say take this one out and put in front of this 3 neutrons. Mass is 1, 0. Okay, guys? Make sense? Make sense, guys? That's a little bit tricky, but you have to know that you don't have radiation that have X3, atomic mass is 3. When it comes like this and the atomic number is 0, then it immediately your brain has to go through neutron. Those are 3 neutrons combined in one here in your X. Correct? So, everybody has this? Everybody has this? Everyone? Everyone? Okay, let's take number 9. Number 9. So let's take number 9. So what will be here our X? What's the atomic mass? Atomic mass is what? That's iodine will give you xenon, correct? Iodine will give off some radiation. We'll see what type of radiation coming off. So what's the atomic mass? 0. What's the atomic number? What's that? 1? Look at it. Is 1 or minus 1? Negative 1. So this one is what we call it? Come on, guys. That's a beta, correct. So E, atomic mass is 0, the charge or atomic number is -1. That's a beta radiation. Okay, guys? It's a particle. So, number 10. So we have alpha radiation coming out. That's alpha radiation, atomic of helium, 4 atomic mass, 2 atomic number. So what will be our X here? What will be atomic mass in the top? 2 what? 235. That's 239. 235. Correct. What will be atomic the atomic number? 92. 92, you know, that came out before. That's uranium, correct? So this one here, our X is here, uranium. 92, 235. That's the most abundant isotope of uranium. We have uranium 235 and 238 and 236, but that's the most abundant. That's what we are producing a nuclear bomb out of it. So the last one, what will be here? X. Atomic mass, how much? 0, correct. Atomic number is what? Is 1. I will say +1. So this one is what? What we call it? E is 0, +1. This is what? Positron, correct. So any question about this? Any question? So you can expect something like this will come in the quiz, will come in the exam, our home one, and then it will come in the final exam. So we have to know how to balance it. And if you are going for health-related programs, you have to know how to do those, because there are equipment inside the hospital or clinics with the gamma radiation. They fight tumors. You heard about somebody is curing his cancer by radiation. Radiation most probably is gamma radiation. Okay, not the other ones. The other ones cannot fight. The other ones they bounce out or be absorbed inside the body itself. But gamma can go through. Gamma can go through, correct? And the dosage has to be under control. If somebody will run the dosage very high, the patient will be barbecued. Charcoal, there will be nothing out of that patient. So it's highly energetic with very, very high temperatures. So it can cause really charcoaling a patient. So any question about this now? Any question? If you don't have any question, we'll go for the next new chapter. So any question before we go for the next chapter? About chapter 3, nuclear chemistry. Those are the major applications, balancing, and type of those radiation. Those are the 3 major topics of the whole chapter. And the most important thing is how to balance nuclear equation, which is totally different from chemical equation balancing, correct? So balancing nuclear equation is totally different from nuclear. Okay, so if that's the case, then we'll go for the next chapter, chapter 4. So everybody agrees, chapter 4? Well, chapter 4 about bondings. So chapter 4, bondings. And this one is not nuclear. We'll have to put emphasis on this. That's a chemical bonding, not nuclear. Okay, we don't have bonding with nuclei in nuclear chemistry. So, well, it turns out to be that, as you can see, elements, the metals, they tend to give off their valence electrons, tend to give away their valence electrons. For example, aluminum in group 13 minus 10 is 3. That's a 3B in the periodic table. We have A and B, that's a classical one, which is I like more than just a normal from 1 to 18. It's very good, but 1 to 18 will give you the whole sum of the electrons there, but it will not give you the information about the valence electron. A and B will give you the number of valence electrons. So aluminum in group 3B. 3 means the valence electrons are 3. Carbon in group 4B. Carbon has 4 valence electrons. Then you have nitrogen. Nitrogen in 5B. Nitrogen has 5 valence electrons. Oxygen in 6B. It has 6 valence electrons. And fluorine in 7B has 7 valence electrons. Then helium in group number 8, it has 8 valence electrons. The old classical A and B definition of the periodic table has advantage on giving us information about the number of the valence electrons. So each element within this group will have the same number, will carry out the number of the group valence electrons, correct? So that's what really is all about. So aluminum in group 13, of course, you know, group from the top to the bottom. Group 13, then say 13 in the old, this is new periodic table. New periodic, that's not in the book, that's periodic table. So 13, but 13 minus 10 makes 3, and this is 3B. 3B is old periodic table. That's an old one. So it's, and 3B means aluminum has 3 VEs, valence electrons. I like both, but then when it comes to valence electron, I use A and B. So I minus when it comes to 13. Okay, so 1 and 2, and then it jumps all this to 13. Then you start subtracting 10 out, so it will give you the number of the valence electrons. So aluminum is in the group 3B, so it will have 3 valence electrons. So aluminum then can go, because it's a metal, correct? And it tends to give off this 3 electrons. It will come out to be 3 positive plus 3 electrons are given off, correct? So those are the VEs. Those are the VEs, valence electrons. Okay, guys? That's all the metal, no exceptions. The metalloid is an exception. Metalloid is behaving, depending on the conditions, they behave as a metal or metals, or they can behave as non-metals in different conditions. So metalloids are totally a different story from the metals. But metals, if I say metal, it means this element has to give off its valence electrons. It has the ability to give off valence electrons. It does not take in, correct? But it gives away its valence electrons. So therefore, we say sometimes they call it in some books or textbooks or e-books, those metals are VEs donors. VEs, metals are VEs, valence electrons donors, because they donate really, donors. So they really donate their valence electrons without any force, without nothing. Just if you put the metal near non-metal, you will see the metal without, it's welcoming the non-metal by giving its free will. So it's not forced to give away its valence electron But by nature, metals are always, if it has near it is non-metals, it will give away, donate its valence electrons. So the non-metals, on the other hand, is taken in, not giving away, is taken in those valence electrons from the adjacent metals, correct? So let's look at the non-metals. Any question here? Any question? Any question? Okay, let's look at the non-metals. Let's look at the non-metals. The non-metals, sometimes they are written as one word. In some textbook, they don't like this. And they like it. They like to write it. Either way, you'll see this is just one word or two words, but it depends on what the author of the textbook. So the non-metals are taking in the VEs from adjacent metals, from adjacent okay, so if I have, for example, if I look at any of those here, one of those, for example, oxygen or nitrogen. So oxygen or nitrogen as an element, it looks like oxygen group 6 what? 6b, and this is 5b, correct? So this is 6 means what? Add to it 10, that's group 16. Add to it 10 will be what? Group 15. That's a new periodic table, BT, and this is old periodic table. So the old one I like because sometimes, I mean, both of them are good, but the old one gives us the exact valence electrons. So oxygen in the 6th group, meaning oxygen has 6 valence electrons. So always tend to have octet rule. Always the nonmetals always like to be having 8. So 6, how much is missing? 2, correct? That's, remember, it has 6 electrons to begin with. 6 electrons. So it will take in 2 electrons, it will make 8. So 8, then oxygen will appear like as a negative charge. We call this one here anion. And the aluminum here, when it gives away its 3 electrons here, valence electrons, 3 plus here, this is called cation. Cation. There was a multiple choice long time ago, definition of cation, and one of the multiple choice, cation is a cat plus ion. Cat plus ion. So make sure you don't fall in this trap. Cation, cations are elements or metals that losing their valence electrons. Anions, those nonmetals, they are gaining valence electrons. So this here, it will have what? 2 extra electrons. To make it what? To make it, this one now has 8 valence electrons. Nitrogen is in the 5th group, or 15 here. 15 here, so 15, 1, 5. 15, so it has 5 valence electrons because of the 5 here. 5 valence electrons, it will tend to have 3 more, so nitrogen will come out to be N3 minus, and it will have 8 electrons, 8 valence electrons. So why is this 8? Why this 8? It turns out to be this called octet rule. Octet means 8. Elements want to have 8 valence electrons to mimic the electron configuration of the noble gas, group number 8. Group number 8, they have 8, except for helium. They have 8 valence electrons and the most chemically stable elements. So this one here, the most stable form of nitrogen as anion, and this is the most stable anion of oxygen because it has 8 electrons. So octet rule is elements tend to have 8 valence electrons to mimic the electron configuration of group number 8, the noble gas elements, okay, which is, except for helium, helium has only 4 valence electrons. But argon and all the other ones, they have 8. From argon all the way to radon, they have 8 valence electrons, except for helium. Helium is exception. It has only 4. It has only not 4 atomic mass 4. It has only 2 valence electrons. So 2 valence electrons. So anyway, so that's what we mean by octet rule. So octet rule is the elements tend to have 8 valence electrons in total to mimic the chemical and the physical properties of the noble gas group, except for helium. Correct? That makes them very, very stable, very chemically very stable. Even metals, aluminum. How many use aluminum? What's the atomic number of aluminum? Let's do this. Let's we saw this one here. We'll see both how the octet rule is working for both. So can I take this one out? We'll do aluminum and maybe oxygen. Can I take this one out? Everybody has it? Everybody has it? Okay, let's do oxygen first and then aluminum. SBDF electron configuration. So oxygen, how many is valence electrons? 6, correct? It has 6. Atomic number is what? What's the atomic number?
8.
Atomic number is 8, but it has 6. So you said 8, so 8 atomic number. So let's see. 1s2, 2s2, 2p, that's 4 and 4. Okay? So that's oxygen here. That's what? That's oxygen here. So guys, so the last one here, so the valence electrons, those electrons found in the last outer shell, in the second one, 2s2, 2b4. Correct? Everybody's following? Now to make it more stable, oxygen 2 minus will be, you add 2 more electrons to it, correct? So if you have oxygen here plus 2 electrons, you get this one here. So this one will be 1s2, 2s2, 2p what? 6. This one here is 8. See how stable this V is. Now aluminum is the same thing we'll do. That's non-metal. Aluminum is, what is the atomic number of aluminum? What is it? How much? Somebody will tell me. How much is it? Aluminum? Is it 13? 15? 13, yeah. So 1s2, 2s2, 2p6, that's 10, 3s2, 12, and 3p1. Okay? Now, Al, 3 plus, will lose how many? Will lose 3 electrons. So the Al3 here is losing 3 electrons, will come out to be 10 instead of 13. It will be 10. So that will be 10, will be 1s2, 2s2, 2p6, that's 10, 3s, yeah, no 3s, so that's it. That's Al 3 plus, correct? 10 electrons because you have lost 3 of those, so that's Al3. So what's the valence electron of Al3 plus? Is 8. Again, is what? Is 8. 3 plus here. That's 8. So those are 8. So that's the octet rule. Octet rule the elements tend to have the most stable characteristics, chemically and physically, by obtaining the characteristics of noble gas, group number 8. So I think I'll stop here because 2 chapters. I'll give you a couple minutes off today. Unless you want to continue, I will continue then. Let's take off, and then Thursday we'll come and finish up chapter 4 by going to the covalent bond. We do the covalent bond.